Our next session before lunch is a little bit about Python. And so we're going to talk about the Python programming language. Obviously, this is not something where we can cover it exhaustively in one session. My goal is to get you guys set up so that you can start experimenting with Python, playing again, and learning a little bit about how the system works so that if you choose to use this, or if you decide that this is something that can really help your research, you're positioned to follow some of the online tutorials, and you know where to look to learn a little bit more, right? And so again, I can't compress an entire semester's worth of a programming class into one and a half or 1 hour and 15-minute session. So we'll do what we can, and we'll start by sort of introducing what is Python. Why is it useful, particularly for scientists? And simply put, Python is an interpreted programming language. And so that's different from something like what you would call a compiled programming language. And so for a compiled programming language, that's very similar to what would traditionally be called something like C or Fortran or even assembly, where you write code and then you have a special program called a compiler that takes that code and translates it into something that your processor can understand. And when I say something that your processor can understand, this is going to be the specific instruction set that might work on an Intel system or an ARM processor, or if Macs were running PowerPCs, although I guess now they're running more ARM, or the newer Macs are, I guess, running ARM, and the older Macs ran Intel. And so it would take that set of instructions and convert it into something that would run, you could think of as directly on the processor on the machine. And if you were to try to read that compiled program, it would look like gobbledygook, right? It would be written for the machine and not for human consumption. Python is an interpreted language, which means you still write code into a text file somewhere, but instead of being compiled and running directly on the processor, so to speak, it's being interpreted. So another program, once again, will look at your code and basically parse each line step by step by step and say, okay, he's telling me to print something to the screen, or she's telling me to write something to disk. And so it will follow those instructions step by step by step and convert the code to machine language indirectly. So it goes through the interpreter, which then outputs how this code should be run on the machine. The advantage to interpreted languages is that I can have, as long as I have the Python program or the Python interpreter running on my machine, my source code can be the same, whether I'm running it on a Mac, whether I'm running it on a Chromebook, whether I'm running it on an Intel system or Linux. It doesn't matter, because the Python interpreter is what's compiled and is converting your Python code into something that is running basically on the machine directly. And so that's the distinction. And Python programs are generally going to be user readable, right? So since they're never compiled, so to speak, they're going to be something that you can look at later on and go back and say, oh yeah, no, I know what this is doing. And if you send it to a colleague, they can look at the code and say, oh yeah, I understand how they're arriving at that calculation. And so Python is an interpreted language. Other interpreted language would be something like Lua or Lisp. Perl is another very big popular one. And so they're not compiled. Other compiled languages would be something like C or Fortran. Or C++, right? And so the disadvantage of running an interpreted language is that it's going to be a little bit slower than what you would get if you were running something as a compiled language, right? So a compiler can take your code, look at it, and try to make all the optimizations that are specific to that particular hardware and try to make the code run very, very quickly. An interpreter basically can't do that. It can't look and say, oh, this person is running an Intel processor with vector extensions, and so therefore I can handle lists of numbers very efficiently. It's going to basically do the same thing whether you're running it on an Intel machine, or whether you're running on a Mac machine, or a PowerPC, or one of the older processors, because it can't make that distinction in the Python language itself. But there's some significant pros, and the fact is computers are fast enough that these days that you generally don't need all of those optimizations to get everything to work right, or at least to complete in a reasonable amount of time. And so you do a payoff, and the payoff is that as a result you get something that's very easy to write and very easy to read. And that's probably the number one advantage of Python. Most of you have, who's programmed in Python before? Raise your hand. Okay, like a fair number of people. So most of you who have never programmed in Python before, maybe even never written a computer programming language before, could look at a Python script and you would probably be able to get an idea of what it's doing. It's that simple to understand. Now, there's some limitations there, and I'm not going to make that statement across the board for everybody, but the advantage to Python, at least in my opinion, is I can go back to code that I wrote 15 years ago, read it, and even if I haven't looked at Python in a while, I could say, oh yeah, that's exactly what that code is doing. And that's the bad code I wrote as a graduate student, where it wasn't well documented and there wasn't comments and stuff like that. If I go back to the best code that somebody else has written from Perl, I have no idea what that means, right? It's a great programming language for text processing, but it's about as comprehensible as some foreign language. And so Python's real advantage is that it's very clean, it's very simple, and even if you walk away from it for a while or don't have all the experience of programming, chances are you can look at somebody else's code and kind of figure out what it's doing. Whereas many other programming languages, that's not the case, right? And so other advantages that most of you, particularly if you're running a Mac, you already have a version of Python on that computer. It might not be the most recent version of Python, but it's going to be a version that you can use. It also has a huge library of standard tools that you can draw from. And so this means that you don't have to reinvent the wheel. So for example, I recently had to write a program that parsed a type of file called an XML file. It's very similar to HTML, what you see on the web. And I could have sat there for a day or two and written my own XML parser that would convert that text file into something that I could understand and read from. But Python already has a library to do that. I basically just looked up the documentation for that library and used that library and basically parsed an HTML or an XML file without having to do any kind of coding myself. I could just start immediately from, let's read this file and start making sense of it. And so Python has lots of libraries like that. It has a standard math library. It has libraries to do very common string manipulations, where if you were working in Fortran and you wanted to say, hey, give me the first 5 characters of this string, like say you give it a sequence and you only want to spit out the first 5 characters, guess what? You're going to be writing code to parse that string and spit out the first 5 characters, because Fortran doesn't have those kinds of libraries. And so Python makes a lot of this stuff super easy to use, and it's the kind of thing where the more you know about the features, you don't have to reinvent the wheel. And so you don't have to learn about sorting algorithms. You can use the Python sorting algorithms. You don't have to learn about how to write a random number generator. The one that comes with Python that's built in is pretty darn good. So it saves you a lot of time, and then there's lots of people out there in the community writing code for math and science and bioinformatics that you can also draw from. And so we'll show you how to install some of those packages as well. Bring up my pointer here. And so you don't have to learn all the nuts and bolts of how a computer works. It hides those from you, and so you don't necessarily get the performance benefit of knowing all that. But again, if it finishes in 5 seconds or 6 seconds, I'm okay with that, right? I don't need something to finish in 2 milliseconds if I'm going to walk to the bathroom and come back anyway, and it'll be done for me, right? So you got to sort of keep in mind that we're not writing Python code that's going to perform at the absolute bleeding edge of computer performance. But if you're trying to write something quick and dirty to process 10,000 text files, and it can get through those text files in 2 minutes, it's a pretty good win in my book. So some other things that might be sort of disadvantages is that Windows support isn't quite as good, although it's getting there. And the Python version for Windows is actually pretty good once you get around some of the tweaks that Microsoft has decided to do. And then like if you really want to do those technical tasks, if I want to directly write to, say, my video card, or if I directly want to write to some kind of memory position, and I know I want to write to that byte or not, that's a little bit more challenging, right? So C gives you direct control of all the memory on the computer, and therefore you can write to different pieces of hardware, and you can do really weird stuff. You're not going to be able to do that so easily in Python. And then, of course, you still have to learn it, right? There's no way to getting around the rigor of thinking about how to program a computer. I find that programming is something that pays benefits in the fact that it teaches me to be more disciplined in how I think, right? So when you tell a computer that you want it to do something, computers are really good at certain things, but they're really dumb, right? And one of my early professors when I was a freshman said something to the effect of, computers will only do what you tell them to do. And that's absolutely true, right? And so if you run a program and it's not doing what you want it to do, it's not the computer's fault. It's your fault because you haven't told it what to do correctly. And so thinking along those lines, developing the framework where you can say, okay, if I want to complete this task, first I have to do A, then I have to do B, then I have to do C. That kind of discipline of thought is something that's obviously helpful for writing a computer program because that's what they understand. But the other thing that it's good for is thinking about science, right? And so being able to program well helps me to write better protocols when I publish papers. Because I think about, oh, what are all the contingencies? What do I really need to tell this individual if they're going to be able to successfully perform this experiment? So it makes you a better thinker. And one of my other professors, my PhD advisor, he used to say that writing code was just another way of thinking. And so it's basically teaching your mind to think in a slightly different way. And so while Python is great to learn, any program is going to help you develop that discipline, and you'll be able to think a little bit more precisely about things. Now, getting into Python, again, we're not going to rehash all of this. But just so that there's not so much confusion, there's different versions of the Python interpreter. For many, many years, Python 2 was the standard. And then back in about 2001, 2002, a version of Python, Python 3, came on the scene. Most computers will still have both installed. There's such a legacy code base with Python 2 that if I go to my Linux system, which is really only, the operating system is only about a year old, it still has Python 2 on there because there are processes and software that require Python 2 that won't work on Python 3. But more and more of that is being converted over to Python 3. And for most of the code that you would write or that I would write, it makes no difference. There might be a couple of parentheses that you have to add. It's not a hard conversion to switch from Python 2 to 3. And some programs will actually run on both, and it'll be just as fine. So the main thing I would suggest is if you're just getting started, unless you have a really good reason, I would start by learning Python 3 because, again, that's the currently supported version. Most of the code has been sort of translated to that at this point, and you'll save yourself a little bit of headaches from potential differences. New features are being added to Python 3, whereas Python 2 right now is kind of in a legacy state where they'll fix bugs, they'll update the software to make to correct problems, but they're not going to say, hey, let's introduce this cool new feature into this version. But right now, the current version of Python 2 is 2.718. The current version of Python 3 is 3.9.5. And like I said, many code features will work in both. The syntax is very, very similar. Again, you can look at both and sort of understand what they're doing. But it's all the stuff under the hood. And so I actually have some code that we use for molecular simulations that is written in Python, but it uses a C substructure to do all the stuff that really needs to be fast, right? And so that's stuff that I've written a long time ago and simply don't have time to convert to the new Python 3 substructure. And so I'm still using Python 2 for that reason. So under the hood, it's a little bit different, but the stuff that the user would use, the interpreter itself, looks very much the same. The reason for doing this was because there was a big discussion. I don't necessarily agree with everything. in that discussion, but they basically said, hey, there's 7 different ways to do this in Python, or in Python 2, and all these really, really smart people were figuring out the fastest way. Like, so what's the fastest way to go through a list, right? And so there'd be 7 different ways to go through the list, but there'd only be one fast way to go through the list. And people would say, oh, well, you're doing it wrong because you're not doing it the fast way. And so Python 3 actually eliminated some of those features, but made things more consistent in terms of, it wasn't so confusing to the user. Hey, why when I change this, range to an X range, does my code now run 10% faster? And so it helped streamline things and make the language a little bit more consistent so that there might be fewer ways to do something, but it was always obvious which is the fastest way to do it, or the user wasn't so perplexed because of that. Okay, so if you already have a computer, you likely already have Python. And I say that even some Windows installations will have it these days. But if you go to your Mac and you open up that command line like you were doing for Xterm, and you type Python, or sometimes if you type Python 3, because again, you sometimes have to make that distinction, you might find a Python interpreter there. And so if I go to one of my servers and I type Python, you can see it brings up the Python 2.7.18 interpreter. And if I type Python 3, it brings up Python 3.8.5. Now, those aren't the newest versions. That's generally not going to be the problem. Oftentimes, you're not going to have the opportunity to update to the latest version, and you don't want to spend all your time updating software anyway. So if it's working, leave it alone. These versions are perfectly fine. If I go here to my, if I go here to my Xwin, so again, if you have the Cygwin installed, and I open up my Xterm and make the font size something that I can read, and I type Python, it's going to bring up Python 3.8. Now, if you didn't install Python from the Cygwin installation program, it's actually very easy to do. You just go to the list of packages, you find Python, you select the version of Python that you want to install, you hit Next, and it's going to go through and install. So you want to keep a copy of that Cygwin installer. Not only does rerunning it from time to time update things if there's updates to the different packages, but you can go in and you can go back and reinstall packages that you might have forgotten about, or that you realize, oh, this would be really helpful for me. So within Python, once you start it, under Linux, or if you're under Cygwin, you can type Control-D to get out. And that should work for a Macintosh too. I think Control-D is basically telling Python that, hey, I'm done with you. And Python used to have, if I typed exit, so it said if I used exit with parentheses, or if I type Control-D or an end of file, that's what EOF is, it will exit. Okay, so if I go here and type Python, again, that brings up Python 2. And for this system, if I want to bring up Python 3, I have to type Python 3 directly. And so your systems, I don't know much about Macs or how Macs are working these days. It may be one or the other. But type whatever brings up Python 3. And you want to look for that 3.8, 3.9 in the Python version. Again, on Linux, it's just Control-D to get it back up. If I'm running it on Windows, so if I type CMD in my Start menu, I can hit Enter. Now, this computer I've already installed Python on, but in Python or in Windows, if I type CMD and bring up the command prompt, you could install Python here too, right? And so this is actually great because you don't have to mess with all that Linux stuff if you don't really want to. You can install Python here and it'll work just as well. On Windows, though, it's a little bit different. I have to type Control-Z and hit Enter to quit. And so it's, again, just a different feature. In Linux, the new line is or end of file is a Control-D. In Linux or in Windows, it's a Control-Z. Okay. Installing it is easy, but the problem is that if you're running Windows and you type Python at the command line, it's going to bring up the Windows App Store. And in principle, there's nothing wrong with the Windows App Store version of Python. It just doesn't give you the same kind of context menus that the bona fide version that you would download from Python.org would give you. And so what I would recommend doing is actually just going to python.org. And if you're on a Mac, it's going to select the function or the file, the version that you need. And so you can go here to download, and it'll say download for Windows. So while I'm talking, maybe you guys want to do that because it'll take a few seconds. Very easy installation. I don't think there's anything that you have to do here, except there might be one checkbox. Let me double check. Yeah, so installing it from python.org. And when you get there, you just want to make sure that you double click or you have that checkbox, add Python 3.9 to the path. So you can install now. I think that's probably the easiest option. Just click the install now. It'll install a local version of Python, and then the rest of the things you can do the same. You can leave all the defaults. Now let's go back here though a second, and while you guys are doing that, I can talk a little bit about everything else. If you're on Linux and you don't have Python, and you want to install it, you'll generally need some kind of administrator privileges. And so, that may or may not be a battle you want to pick, but if you have something greater than Python 3.7, you should be fine for almost everything that you would need to do. The other thing is that, somebody had mentioned about, more practice with Linux. At the end of this session, I'll email out, there's actually a couple of places where you can get a virtual Linux machine, in which you can run on a program called VirtualBox, and it's like having, you basically just download a ginormous file, and that file is a virtual hard drive, and you can run Linux on your Mac or your PC, and it looks like you're running Linux, but you're actually running Linux as an application. And so that's one way to get administrator access on your own Linux computer, in which case you would have administrator access, you could do whatever you want. The best example of this that I know about is Frank Delaglio, who maintains NMR Pipe. He has a version of a VirtualBox machine that you can run, and already has all the NMR processing tools on it. There's also a tool called NMR Box. And so I apologize, I'm an NMR spectroscopist, so the way I know about these things is through the NMR community. There might be other people out there that maintain virtual Linux machines as well. I'll do a quick Google search to see if I can find one. But if you do have administrative access, then you can install Python on that Linux machine yourself. The other thing I would do is most of you, if you type Python at the Windows command line, it's going to bring up that App Store option, which is a real pain, in my opinion. And so what you would have to do to disable that, if you hit app execution, or I think that's app execution. If you type that down here in the search box. Now I've already disabled it, but you probably have both of these turned on. And what that does is when those are turned on, it looks at the command line and says, if this person types Python, bring up the App Store. And so by turning those off, you'll be able to use the Python that you just installed or that you just downloaded from python.org, and you'll see it in the command line as well. And so that's the way to sort of turn off Windows hooks into the Python and use the version that you're actually getting from python.org. So once you've installed Python, you'll see something like this, and you'll go through the standard installation. And if you're on Windows, you'll be able here to go to the Start menu. And if you scroll down, you'll see a Python box. And there's a couple of different ways to start Python. If I click on the just regular old Python 3.9, it's going to bring up like this text thing. And that's fine. That might be how you want to work with Python, but probably not. Within Windows, you can actually open up a program called idle. And this is how I recommend using Python on Windows. So if you click idle, it brings up a little bit more sophisticated menu where if I look here, it's the same thing. I can still type Python commands. So if I type print, hi there, It still prints hi there. So I can type directly into the Python interpreter. That's what we're looking at here. This is the interpreter. But I can also go create a new file. And now if I want to type a specific Python program into that file, I can type, again, I can type print hi there. And notice it has some syntax highlighting. So the keywords are going to be in purple, the strings are going to be in green, and that's actually really helpful if, for example, I have a 75-line piece of code. Now, why would you do this? I have no idea, but let's suppose I had this. And let's suppose in one of them I forgot to close the quotation marks. Now if I go down here and start hitting enter, it's going to start giving me warnings. I think if I type new. Yeah, nope, it's still. Huh, interesting. Oh, because I see what it's doing. Yeah. So this would now be in that string. This closes the string. So it's not super smart, but if I try to run it, it'll give me an error because I forgot one of the quotation marks. Yeah. So, okay, and here it's even smart enough to tell me where it was. Okay, so, but if I write a 75-line program, I can now save it in this text file by going up to File, Save. And if I want to run that program, I can go here and I can go into Run, and I can hit, OK, let's run this. I think I need to close that parenthesis. And now I can run it, and it just prints hi there over and over again. Probably the dumbest program you'd ever write. But notice that I can go over here, I can edit my code, I can save this file, and if I just press F5, it runs the code. And so it's a very nice way. Remember when we talked about GNU-plot, and we said having a text file open and being able to do something in the interpreter for GNU-plot was the way to go. Because that way you can just go back and you can type into the text file rather than trying to edit the command line all the time. This is the same way. I have a window that has my code in it, right here. And I have another window that has my output of my code over here. And so now I can edit it, I can change it, I can run it, I can edit it, I can change it, I can run it, and I can go back and forth. And here's one of the key #1 secrets of writing programs. Don't write everything at once. Don't try to just sit down and write the whole program in one go. You will make tons of mistakes, and you will have a real hard time finding them. Always start with the simplest thing. If you're going to start it with a program that reads in a PDB file, don't try to write a whole program to do that all at one time. Write a program that reads the file and then just prints the results to the screen. And don't even try to parse the PDB file. Just practice making sure you can read the file first, and then if that works, then you can build on it and build on the foundation that you know is solid. Whereas if you try to write the whole thing at once, first write the program that opens the file, then you write the program that parses the file, then you write the program that calculates phi or psi angles between the atoms, or then function that does this, and then you run it and it doesn't work. Well, now you don't know necessarily where the error is. But if you always sort of work in small increments, you're going to be in a much better situation to say, okay, that's where the problem is, because up until now I knew it worked, but it was in these last 5 lines of code that I wrote that it doesn't work. Right? This is often called the Knuth test, after a famous computer scientist named Don Knuth, where it says, find the simplest piece of code that fails and fix the problem based on that. And so if you have your code written sort of in simple modules, it makes it much easier to do rather than try to find something that, for example, if I'm reading a whole bunch of 10,000 sequences and I get an error, well, it's much easier for me to work on a data set of 5 sequences if I get the same error than to try to work on 10,000 sequences and figure out what that error is. So find the simplest case where you get an error. And so in this case, for example, if I forget to close one of these quotation marks, again, the interpreter is going to read this and says, okay, here's a print statement. and I'm going to print this string, which is between the quotation marks, and we'll do that first, second, third. And here's a print statement, and now I'm opening the quotation mark, but I never close it, and I get to another print statement. Oh, and here is where I close the quotation mark, and it basically does that over and over again until I get to here, and I close the quotation mark, and now I have this statement here at the end that's kind of left over. And so the computer is going to basically do that. It's going to be much easier for me to troubleshoot this code than it would be to troubleshoot something that's like 30 times longer. So again, computers are dumb. They're going to be very sensitive to things like, I forgot to close this parenthesis. You've all fought with Excel for that, right? You're writing some complex formula in Excel and you forget the parenthesis and it says, oh, error in your formula, right? Computers are kind of dumb like that. They have some tools. So if you look here, when I close the parenthesis, you'll see that the other parenthesis flashes. And it gives you a nice cue that says, oh, you're closing that parenthesis. So they're helpful when they can be. But generally speaking, they're dumb. They're not going to be able to say, oh, I see you intended to put a quotation mark here. They can't read your mind. And so you've kind of got to be very particular about how you work with programming languages. In that sense, it's also similar to the idea that it helps you get more detail-oriented. So remember I told you about changing how you think? This is like anal retentive to the max. But if I have a student in my lab writing a protocol, I want them to be anal retentive to the max, because that means that the likelihood that some other student is going to be able to reproduce that protocol is much better. And so this will train you to be more detail-oriented in your data as well, in your research as well. Okay, so Python, as I mentioned, has a whole bunch of modules already in there. They're usually called modules and not libraries for historical reasons. In other programming languages, you would say, oh, there's the math library, here's the string library. In Python, they're called modules. And as I said, there's lots of people who've written modules that can help you do your scientific programming. And so there's a couple of key ones that I would recommend installing on every piece of, or every Python interpreter that you use. The first is NumPy, or numeric Python. It gives support for matrix calculations, right? So you never have to do matrix multiplication again once you know how to use NumPy to do that for you. Matplotlib, it actually lets you do graphics within Python. And so, I got to be honest, lots of people here have used MATLAB, or have people here used MATLAB? Anybody use MATLAB? Yeah, there's a handful of people. So there's something extremely powerful to being able to type something at a command line and immediately look at the graph, right? Python by default doesn't have that feature built in, and MATLAB costs a lot of money if your university doesn't subscribe to it. We subscribe to it here, but not every university does. And so Matplotlib gives you that feature of saying, hey, I have a function or I have a set of points that I want to plot. Show me what they look like, and you can incorporate that right into your programs. Extremely powerful. Scientific Python, or SciPy, offers some support for function optimization. So we talked about minimizing chi-squared. I'll have a code example that we'll look at. We probably won't talk too deeply about it, but it basically minimizes chi-squared. And it does it thousands of times, right? So imagine trying to run nuplot 1,000 times on 1,000 different data sets. That would be burdensome, to say the least. But within Python, you can write a code, and if you have the optimization code, you can just write it. It might take you a couple of minutes. Maybe you go for lunch and you come back and it's done. That's great, because now your computer has been doing work when you were having lunch. Sweet. And then finally, BioPython, or the bio module, provides functionality for parsing PDB files. And so if you want to say, hey, I want to do some quick calculations on this atom and this atom, and I don't want to have to parse these things manually, BioPython is a way where you can load in a PDB file and you can manipulate it by using the languages of residues and atoms instead of trying to say, okay, go to line 47 and read out column 6, which is traditionally how you do PDB parsing. Okay, so how to install these? Again, we can walk through this right here. Generally, you want to have your Python closed. And for my case, they're both already going to be installed. And so it's going to say, hey, this is already there. But you can type pip if you have it. And most versions of Python will have it. Sometimes you might have to type pip3 for Python 3. And so if I type pip install -upgrade -user pip, so this is basically going to update the pip module. And so pip is the sort of resources that goes out to the web and grabs these libraries for you and keeps them up to date. So it does some of this updating and installation work for you. But I'm telling it to do an installation, so I'm going to install a new module, and really I'm just going to update that module if it's already there. Because I don't have administrative privileges right now, that's what the -user is for. It helps, it just installs a local copy. And I'm going to tell it to do this for the pip module. And let's hope it works. Yeah. So you can see this is its progress bar. You'll probably get a much more reasonable progress bar. But you can say, hey, look, it's installed and it's not on path. I mean, it's giving me some warnings, but at the end of the day, it says, okay, it successfully installed the latest version. On the other hand, if I go here to Windows, I can do the exact same thing. I think here I just type pip. So there's only one version of pip installed, so it's not pip3. And so again, it's pip install --upgrade --user pip. I think that's what it is. And here it says it's already the latest version. And once you do that, now you can go in and you can run these other commands. And so if I type pip install --user numpy, again, on mine, it's going to say it's already installed. But on yours, it will say, oh, I'm going to go out to the web and download that version of numpy for you. And so you'll do it, and this will basically install all of those libraries for you. And now if I go back into idle, and again, these days I really rarely use the start menu. I often just type into the command line, or type into the search bar. And now if I bring up idle, and I type import bio, oops, I guess it's biopython. So if I type Alt-P, it brings back the last line. Maybe it's capital. Yeah, I'm sorry.
I think it's a bio.
Yeah, well, capital bio works too. So, or if I type import numpy, so basically that's telling Python that, hey, I want to make sure that all the numeric Python features are available to this particular program. I can go over into my code here and hit save, and I can go put them up at the top too. Import bio, import numpy. And again, they don't print anything to the screen, but I can run it and it processes it. Now those libraries are available to my code. Right? And so once you have those 4 libraries installed, you're pretty much set for most biochemistry types of things that you might want to do. You'll certainly be okay for running anything that's coming out of my lab or out of my programming for right now. But there's other libraries that you can read. There's some that allow you to parse web pages. There's some that allow you to go out and download files via FTP. So there's all sorts of libraries that you can work with in Python. We're just not going to go into them all. And so once you've installed everything, if you go out and grab SciPy and everything, it's going to download a couple of dependencies as well. And so when you're done, you'll be able to type pip list or pip3 list, and it'll list all of the packages, the external packages that you've installed. Now remember, Python has all sorts of internal packages that come with Python. Those are part of the, download from python.org. This is basically the third-party stuff that's written by others. And if you go in and you do pip upgrade every once in a while, it will update those to the latest version. So if somebody updates the SciPy module, it'll go out and grab that and make any changes that are needed. And so we already seen this a little bit. This is, again, kind of the main goal of this session, is to sort of show you what I've learned over the years, right? So I don't do as much coding as I'd like. Usually when I'm coding these days, it's because a student has a critical problem that I know is that they might not be able to solve, and so I've got to sort of buckle down and write code. Honestly, this type of skill makes students more valuable, in my opinion. Not that I don't value my students, I have great students. But if I have a choice of 2 graduate students that are equally skilled and one knows how to program, I'm actually going to favor the one that knows how to program. Now that's kind of rare. Most graduate students coming into our department anyway don't know how to program. But so much of what we do is handling large data sets and dealing with large amounts of numbers that it's a real benefit, right? It's a way that one student can crank through 7 or 8 data sets in a day versus what another student who doesn't know how to program it might take them a week or more. And so that's not to poo-poo on students. What it is to say is that if you have the opportunity, or if you're not quite done with your undergraduate education yet, take a programming class. You will thank me. And you will not only make yourself more marketable for graduate school, you'll make yourself more marketable in almost any context in the real world. I mean, it's that important of a skill. And so, we're giving you sort of what works and what's helpful, but this is something that you can develop, and let's suppose I have a friend who actually wrote some really important code on doing automated NMR sequence assignments. Fabulous scientist, very successful, published a lot of papers, but decided that he could make way more money working for Amazon in their artificial intelligence division. And how did he do that? Well, he leveraged his ability to write programs and do specific types of programming into a way to get a really lucrative job. So this is one thing that I really feel like chemistry departments aren't doing well. Our chemistry department doesn't have a programming requirement. Most every chemistry department that I've talked to doesn't really require their majors to do this, and I really feel like it's a short-sighted solution, and it's not making their majors as competitive as they could be. You don't have to learn to be like a master coder for this. This is, most of the problems that we solve as scientists are actually quite simple. They're just really hard to do if you're dealing with an Excel spreadsheet that has 10,000 rows. So if you can, learn some of this. Anyway, so the basic way that I can think about for how to do this, and so here's where we'll sort of switch to sort of a more interactive approach, is if I'm writing code, or if I'm about to start a programming session, I'll keep that open for now. What I'll often do on Windows is I'll have my idle window open. And again, if you don't have idle open all the time, but you do have a .py file, you can always right-click on that and you can hit Edit in Idle. This is the advantage of installing Python from python.org, because if you install it from the Windows App Store, for whatever reason, this doesn't appear. So if I edit this in idle, it'll bring up the idle window. The other thing that you can do, and I'm providing for you guys, is here's a Python template, right? So, what we would call in programming, this is like boilerplate code. Almost every Python program that you would write would have some sort of combination or basic features where, you would be parsing or taking a command from the command line. And so you're welcome to download this and use it. In my case, I can probably, so again, I don't think Firefox, maybe it will let me save it. Save page as, save it to desktop. Yeah, so again, lots of things are sort of protecting you from downloading malicious code. So I probably, if I save this to the desktop, oh, it does show up as a .py file. And so from here I can edit it with idle. And so again, when I write code, I usually have a window with my program open. On Windows, it's often using a program called Xemacs. Another program that's similar and that has syntax formatting is Atom. But again, idle's already installed with Python, and so that's usually what I use first. And then, in this case, if I run it, it'll bring up the Python interpreter so I can sort of see what's going on. And so one window will have my code, one window will have my interpreter, and then if I need the web, I can say, okay, how to sort a list Python. Right? And so one thing that's really nice is that the internet's so good these days, you almost never have to go to the original Python documentation. There's lots of web pages out there that give you examples of how to sort lists or how to print a string that has specific parameters. And so I always have a web browser open because, believe it or not, I don't have everything memorized. And you shouldn't work towards that either way. You should try to think towards what's the structure of the code, and then if I have specific questions about how to implement something, a great place to look is the web. And then on Mac, it's a little bit different. I guess that's a typo there. So on Mac, I still have my block window open. So what I'll typically do on Mac, and let's actually do it the same exact thing. So I can go here, and if you've installed Fugu or WinSCP or CyberDuck, you can go in and you can open that and transfer the files. Okay, so what I'll do is I'll copy this template.py file into my home directory. And notice here, if I type ls, I can list all the files in that directory. And you can see, oh, there's template.py. It's right there. Now let's suppose I didn't want to do everything in my home directory. I can type a command called makedir to make a new directory. And in this case, I'll type that command makedir, and I'll call it pytest. And so now if I do an ls, or a directory listing, you can see there's a new directory there called pytest. And Linux is basically built around what's your current directory, what you're going to work in, where are you currently situated in the file system, and everything you type is relative to that current location. It's very similar to having a Windows Explorer window open, where everything you're going to do is within that one Windows Explorer window. And so I'd like to move this template.py file into the directory pytest. Well, there's a command called mv template.py, and then I type to the location where I'd like to move it to, and so I'd like to move it to the pytest directory, which exists in the current directory. And now if I do a listing, note that that template.py is gone. And I just have the pytest directory. So now I want to change the working directory. That command is cd. And if I type cd pytest, I can hit tab and it'll automatically complete it. And now I type ls. And notice that I'm now in the pytest directory. And there's one file in this directory called template.py. Now let's suppose I wanted to run this, right? If I go over here into my idle, running this code is as simple as hitting F5. Right? And so if I hit F5, it says OK here, and it's printing out what the arguments are. If I want to provide some command line arguments, I can hit Shift F5, and it brings up some windows. And so sometimes you want to pass like a file name to your program. And so if I want to pass a file name like myfilename.txt, I can just type it there. And now look, it says, oh, the argument that you passed me was myfilename.txt. It doesn't say whether it's there or not. I haven't written code to do that. Right? It's just telling me this is the argument that you've passed at the command line. Here on Python, on Linux, if I want to do it, I do the same thing. I can type Python 3, and then the name of the program that I want to run. Notice it says arguments are, and it gives me the brackets. Here, if I want to provide command line arguments, I just tack them onto the end. So, myfile.txt. And once again, it shows me that I've given it an argument of myfile.txt at the command line. Now that's how I would run code from Linux. How would I edit it? Well, in Linux, I frequently use the program called xemax. And what's the character I'm going to type at the end of this command to give me my command line back? Anybody remember? Ampersand, I heard it, good. And I'm going to type xemax template.py ampersand, and now it brings up the window. And notice it's not the same format, coloring or syntax highlighting as I have over here, but it's the same idea, right? So xemax is nice because if you have it configured correctly, and you should all have this set up, it gives you some syntax highlighting cues, which makes your life a lot easier when you're trying to look at where strings are and where comments are. And so one thing, notice about this template file, there's a whole bunch of comments, and comments all start with pound signs, right? And so that's the typical way in Python that you say, hey, this isn't code for you to try to interpret. This is code that is there to help me understand what my program is doing. And in here, in any template I recommend, you have the name of the program, your name and contact information, the date, and then a brief description of what that code does. That way, if somebody else comes and looks at your program, they can say, that's what this person was doing. And so by putting this in here, I'm sort of encouraging you, if you're going to use my template, you can sort of change this and make it sort of apply to whatever you're doing. Right? And so now I have the text file. It's open. I can make changes. I can save it. Now I haven't made any changes, so save template isn't available. But now I can have an open window, and then if I want to run the code and see how it's working, I can type Python template. And if I want to make changes, so for example here, if I want to go print, hi there, exclamation point, and Control X, Control S is, Emacs has a whole bunch of funky keyboard commands, but you can always also just go here. And so now that I've saved it, I can run it again. Again, just press the up arrow in Linux. That brings up the last command. And now you can see it says hi there. And so I would go back and forth, make my changes to the text file, make my, run the code, see how it works. And let's see what an error looks like, right? So here, if I run, and I forget the close quotation mark, and in Python, single quotes and double quotes, they have to be matched, but you can use either of them to designate a string. But here I'm going to forget a close quotation mark, and I'm going to try to run that code. And so what it's saying is, hey, look, there's a syntax error. Something you typed in that program isn't working for me. Remember, computers are kind of dumb. They're not going to know exactly what's going on. They're just going to tell you the best they can what error they found. And here it's saying, hey, I reached an end of line while scanning a string literal. So it was looking at a string, and it got to the end of the line, and it started working on the next line, and it said, hey, that person didn't close their quotation mark. I wonder if that's an error. And in this case, it's saying, hey, look, I never find a closed quotation mark, so I'm not going to try to run this code. Or I'm not going to be able to run this code. Okay, so here's the dirty secret. Now, I've hinted at this already. I can't teach you how to code in 1 hour and 20-minute session. We've got maybe another 10, 20 minutes here that I can work with before you guys will throw me out and want to go to lunch. I can't teach you this in one session. We're going to look at some examples in the remaining time that we have, but this is something where, at this point, where you're going to have to sort of work through some tutorials. There's lots of stuff available online. We have some slides to show what I recommend. But generally, you're going to have to sort of go through and practice and develop some of these skills on your own. It's not hard. And the biggest challenge that I find, at least for students that I work with, is that it's not learning code. I mean, honestly, the code is not super hard to learn. It's this activation energy of getting Python installed, figuring out how to work with a text file and how do I run the code in this text file. It's all the stuff that we've been doing here that tends to trip people up, right? And so getting the software on your computer, being able to say, okay, I can type into this and I can run it in Python, that's really, once you have that started, now you can go to almost any Python tutorial on the web and be in a position where you can learn, how to type basic statements, how to develop calculations, how to do, file input and output, loops and everything else that you would need to learn. Now that said, I do have some suggestions for, where to learn. Right? And so, okay, had me scared there for a second. So the first of these is probably a little bit more technical than what you maybe care about, but it's the one that I kind of worked through when I was first starting this. It's how to think like a computer scientist using Python, but it sort of walks you through the basic command structure of the language, shows you how to do things like open files, close files, go through things like loops. I haven't worked through it as much, but I have spent some time looking at this, how to automate the boring stuff with Python, right? And I love this because it basically says, look, we're not here to train you to be, the next Jeff Bezos or the next Bill Gates. 99% of the stuff that people do with programming language is actually really quite simple. And so we're going to teach you how to save time by showing you how to loop through a whole bunch of numbers and do 10,000 calculations that are otherwise identical. Or we're going to show you how to loop through a file and pick out the words that you want. Right? So automate the boring stuff with Python is really kind of what we're often doing as scientists. It becomes impractical for you or me to process NMR spectra if you've got 50 of them. But if you know how to do some coding, you can write some code to do that, and now it becomes much more straightforward. And the other nice thing about programming is that, that's like your lab notebook. If somebody comes back and says, hey, how did you do this calculation? Right? You don't have to guess anymore. You can go right to the code and say, well, I took this column and I added this column to it and I divided that sum by 4. So you can go back and it basically serves as your documentation for how you're doing these calculations. And then the final thing I would suggest here is again, having the Python module index open, right? And so if you're interested, like, oh, how do I deal with strings in Python? Well, you can go to the Python module index and they have some basic documentation. This is a little bit more advanced, but if you reach a brick wall somewhere else, you can always go there, and it's a fairly good reference. This is another way that I really learned because I went to the module index and I said, oh, look, there's a module for compressing files. That's cool. Let's see how it works. And then from here, I'd say you're empowered to go out and you can be that novice programmer, that newbie programmer on the message boards on the internet. Most people are very nice, very kind. The other difference between Python and Perl is if you go and talk to Perl people and post on Perl message boards, they're all a bunch of kind of assholes, right? And so, it's really silly. It's like, hi, I'm learning how to use Perl and I can't figure out this, and they'll be like, why aren't you using the latest version of Perl? And it's so obvious if you're just using this construct. And it's like, guys, come on, these people are trying to learn how to code. The Python community I found is very supportive. And I've posted some, I think actually if you Google my name, you'll find me on a couple of these message boards, probably from like 10 years ago. But anyway, so people are generally supportive of this kind of stuff. And so you shouldn't be afraid to ask questions. Now, if it's been asked 30 different times, somebody might say, hey, look, there, I Googled this for you, right? So check it with Google first. But generally speaking, if you have an error that you can't figure out and you have nobody in your sort of local support community that can figure out either, it's not bad to ask questions on the net. And the two forums I provided there are probably the main two for Python programming. Okay, and then a final quick note about emailing code. And so my group has run up against this. Yours might too. Our email system here if you try to email a .py file, it's going to say, oh, that's executable code. We're not going to email that. That's a security risk. And again, it's probably a good thing. You don't want people running random programs that they're receiving over email. So if you're trying to email code to your advisor, or your advisor is trying to do that to you, rename these are just text files. So you can just rename the .py to .txt, and most email systems will just let that go through as a regular text file. You can email Word documents, you can email Excel files, but if it's a .exe or a .com or a .py, because there's the potential for that to have malicious code in it, most email systems these days will flag it. So just make it with a text file ending, and that way you can get them through. And just tell your reader or your recipient, hey, this is a Python program, but I renamed the extension with text. OK, and so in our final time here, I just want to show you two examples. One will give you an example on how to run some Python code. The other will give you an example of something that's actually quite sophisticated. And it'll show you how Python can do something like what nuplot is doing. And if you're interested in how nuplot is working under the hood, it kind of gives you a picture into that. So I've provided two pieces of code on the Biochemistry Bootcamp website. One of these is code for replacing the B factor column in a PDB file. And so remember we talked about yesterday with the PDB, there's a file in there that has the temperature factor or the B factor, and maybe sometimes you want to replace that with code that you or numbers that you've calculated from your experiments, right? And so this code will do it, and I've provided some examples there. And then I provided another program which is a lot more sophisticated and probably a lot more buggy that does some model optimization. And we'll look at that very, very briefly. And I'm not going to try to explain it because I think it would take up all of our time and wouldn't be helpful. But we can look at these. Again, I think from this point of view, I'm going to use the Windows PyMol, or Windows Python. And if I go here to desktop, so you can be downloading those files if you want to follow along with me. No, this is session 12. And in Windows, the directory listing command is dir, and I always get those mixed up, so I type ls at the Windows terminal all the time. Anyway, so first of all, let's look at the 2OED BFAC program. So I'm going to just open that up in idle. So I can right-click it in idle, or if you're on Windows or on a Mac or in Linux, you can just open it with your text file or text editor. And so basically this program has a couple of different things. And again, we're not going to go through all of this, but generally the structure of my programs has a section where it handles user interface. So that user interface, in this case, it needs to know what the PDB file is. It needs to know where to read the P factors. It needs to know what the new PDB file should be. And then if there's multiple chains in that PDB file, it needs to know what that is, right? And so you're just thinking about, how would I need to solve this problem? What information would I need to replace all the B factors in a PDB file with those from another file? So well, obviously I need the original file. I need the values that I'm going to use. And I need to basically say where to put the output. And in this case, the chain is optional. If I don't give it a chain, it'll just use the first one it finds. You can see up here, basically all the PDB parsing is done by this property of the BioPython module, where I can open up a PDB parser, I can get a structure, and here PDB is the file name that I'm using. So basically this creates an object that corresponds to the PDB file that I'm reading. And now I can go through and look at the first model. And at this point, it's basically just iterating for every residue in the chain, read in the residue ID, match that to what's in the table that I provide, and then apply the new B factor to that residue ID. So that's really the logic of how this is working. And then there's some additional code that actually loads the values from the file that I provide. So let's see how I would run this. Right? So here I would type Python, and most of my code, if I type pdb bfac, oh, I don't have to type Python 3. Right? I give it a little bit of usage information, and you can sort of see how that's coming in down here. Most of the code that you guys write will probably not be quite so user-friendly. But again, I've done this for decades, and so for me, adding something like this to my code takes about 2-3 minutes. You don't have to write everything so that it's super user-friendly, but since I'm often doing it for you guys or for my group, I want them to be able to sort of have some help if they need it. And so here again, it's sort of telling me how to run this program. Again, I'm just going to press the up arrow key, and in Windows that works too. And so the PDB file I'm going to run is 2OED. I believe the B factor values are given in 2OED BFAC. And again, what is this? It's just a residue number and a B factor. So again, you could make this in Excel. Actually, that's how I made this file, and I just pasted it into a text file. And so 2OED, or I'm sorry, yeah, what is it? 2OED bfac.txt. And then my output, I'm just going to call output.pdb. I'm going to not worry about the chain. And so, OK, it didn't give me any errors, so that's good. And if I look now in my directory, I now have a file called output.pdb. And if I open that up in PyMol, well, it looks the same. That's because I haven't colored it by B factor. And so remember, we talked about how do you have to color specific residues. The way to do that in PyMol is with this command called spectrum. And I can run spectrum B, and then min is going to be 0, max is going to be 100. And I think I have to give it a gradient scale to use. So let's do blue, white, red. Nope, that didn't work. So I can type help spectrum. Again, I don't remember all this either. And so, OK, so here it's not min, it's minimum and maximum. So minimum equals 0, maximum equals 100. OK, and that seems to work. Here's all the different spectra or the palettes that you can use, so the gradients. And if I hit escape, it's very patriotic GB3, right? So again, now think about how you might use this in your own experiments. You know, maybe you can associate each one of these residues where if you mutate it to alanine, you've knocked the activity down, right? That's a lot of mutations, right? Even for this, it's 56. But you could put those activity numbers in the B factor and then plot that on the molecular structure and say, look, these are the residues that influence the function the most, right? So that's one way you could use this. And again, once you learn a little bit more Python under your belt, you'll be able to go in and make changes to this if you want and tweak it as you need to. The other code that I'm going to show you here, and again, we're just going to basically take a look because it's pretty complicated. I wrote this probably over the series of maybe 2-3 days. But this is a fitting algorithm, and it's designed to take some fluorescence data, so specifically the fluorescence signal of a protein as you add guanidinium and you denature that protein. And it's basically designed to extract a delta G of unfolding from that data. And so it does the chi-squared minimization and finds the best fit values, just like you would do using Excel. And you could implement the first part of this in Excel. But then it does something called bootstrap simulation. And basically what it's doing with bootstrap simulations is it's taking your original data points and generating 1,000 new data sets where some of them they might resample the first data point a couple of times and leave the second one out and include the third one, but then forget about 4 and 5. So it's generating a whole bunch of artificial data sets. And if you have one data point that's really locking down the fit value that you're getting, by resampling your data sets in that way, you're going to get a much better estimate of the uncertainty of your fit based on the data that you've provided. And so this fitting program is doing all that. I have to provide some physiological constants, so the temperature. I have to provide a whole bunch of information. And then eventually when you get down here, it starts reading in the data file. This program doesn't take any parameters, and so we're just going to run it. So Python, oops, yeah, whatever. Python fitting. And one of the things we didn't talk too much about is that when you're doing a model fitting, and we did it implicitly in all of our model fitting that we did in class or in the session, you have to provide some initial guesses for the parameters. And so the very first thing this program does is it spits up a graph and says, how good are your initial guesses? Because if your initial guesses are crazy, if you're guessing that the delta G of unfolding is 30,000 kilocalories per mole, which again, you may not know that that's unreasonable, but it is, you're going to get something that doesn't look at all good. And so you want to use those sort of initial guesses to get kind of close. And this is showing that, yeah, we're kind of close. It's going to get better. So let's remember what this looks like. I can close this window, and it's doing the initial fit, so that was very good. My initial chi-squared is 133. My reduced chi-squared is 0.27. So remember, if that's less than 1, that's actually really good. And then here at the end, it's providing uncertainties, percent errors, and the main one that we care about is delta G. And so this is telling me that the delta G of this unfolding transition is 5.7 kcals per mole with a standard deviation of about 0.32. So 5.7 plus or minus 0.32 kcals per mole. And then it calculates some confidence intervals. There's a whole bunch of new files here. The one that we're most concerned about is fit.pdf, which shows you the new optimized fit. You can see here it's going through all the data points. And I can also open up, for example, we talked about this bootstrap. I can look at a histogram of all the delta G's from that bootstrap. And this histogram is basically how it's generating the uncertainties on delta G. Right? Again, there's about a semester's, well, maybe not a semester, a couple of weeks worth of statistics going on here. But at this point, you can sort of see how Python can be used to do something very useful in a way that, we can modify this code and use it for all sorts of types of fitting applications and get estimates of uncertainties. So hopefully, again, you won't know much about programming in Python from this session. But hopefully you'll have a taste of, one, how to do it yourself, where to go next, and then sort of see the power in doing some of the types of problems that you might come across in your own research this summer. Any questions? We're right about where I wanted to end. I knew I was going to end a little bit late, but this is still about noon. And so questions? So I think the best way to try this is to learn more is to go try this yourself. See if you can't do the exact same things that we just did here if you haven't been following along. And then, once you get there, then you can start trying to type your own simple programs. And, don't try to start with the hardest problem in the world. Try to start with something super simple, like print the value of 2 plus 2 to the screen. And then from there, you just work your way up. And eventually, you'll be writing super complex stuff like this in no time. OK.